welcome Anush ji for the workshop. Welcome on board.
Yes, thank you very much. I hope you're fine, doing well.
So participants, we have our speaker on board. So without any further delay, it will be a great pleasure to introduce Anush K. Chandrappa. Dr. Anush is working as an assistant professor in School of Infrastructure, IIT Bhubaneswar. He has completed his MTech and PhD from IIT Kharagpur in the domain of transportation engineering. After his PhD, he worked as senior engineer in Dilip Buildcon Limited, where he was involved in road construction and design projects across India. Later, he worked as an assistant professor for a short duration in Thapar Institute of Engineering and Technology. His research interests encompass asphalt and concrete pavements, focusing on sustainability, low impact development of innovative products, payment evaluation, etc. He has more than 50 research publications in international and national journals and conferences. He is involved in several research and consultancy projects at government and private organizations. We welcome you, Dr. Anush ji, and the platform is to you to present your talk.
Thank you very much, Raviji, for introduction. So I will stop my video and share this presentation now. Just stop Can you all see my screen? Raviji, can you see my screen?
Yes.
I'm on full screen mode now.
Slide share mode.
Now it's full screen mode, slide share mode, right?
Yes.
Okay. So first of all, thank you, Professor Dubey and Dr. Raviji for inviting me for this lecture on decarbonizing India's transport system 5-day workshop. Today, we will discuss on sustainable application of waste cooking oil in asphalt mixtures towards circular economy. So today's speakers involve myself and our scholar, Mr. Shobhit Jain. In the morning, already we have seen Dr. Biligiri talked about circular economy in payments. So now we will see basically how we can use waste cooking oil as a rejuvenator in the asphalt mixtures and what benefits we get from this waste cooking oil in asphalt payments. So moving on, as you know, India is home for almost 1.42 billion people and currently stands first in the world with highest population, surpassing China recently. Now, as we know, as the population increases, the amount of food demand also increases. Now, generally, studies have found that the way we consume food, like urban and rural population, have different food consumption pattern. And due to this, the urban population, due to the sedentary kind of work life, they basically consume more fried foods where edible oil is used to fry the food. So this way, currently, India consumes almost 2,700 crore liters of cooking oil annually. It's a big number. The question arises, when we use this oil after certain frying cycles, what happens to this basically oil? Let's say you whenever you cook in a home, let's say you make some dish where you fry, maybe puri or any kind of item. After a certain number of frying cycles, we cannot reuse it because it turns black, it becomes unhealthy. So the only solution what people do is they will throw it to the kitchen sink. So this actually has caused several impact in the long run, which we'll discuss in subsequent slides. Now, generally, FSSAI restricts up to 3 times to use cooking oil. For example, we can use at max 3 times to cook any food with a particular oil. Beyond what happens, if you use multiple times, it may cause chronic heart diseases, increased blood pressure, and other health-related issues. In addition, repeated using cooking oil will actually change sensory properties, like it can become more bitter, it can actually produce more aldehyde, which is not good for our body. So basically, what happens to cooking oil after 3 cycles of usage? As I told you, we are spending almost 2,700 crore liters of cooking oil annually. This huge amount of oil, after 3 cycles, what is this being done? Right? And then what are the current practices of disposing it? How are you disposing? If you see any common household, even my house also, I would say, we generally dispose in the kitchen sink. It is actually a very bad practice because when the oil goes to the kitchen sink, it actually clogs the sewer drains in the long run. Right? And what is the environmental impact of this waste cooking oil? Right? Are we basically, if we dispose it in the sewers or if we dispose it in as a landfill or as a water body, what impact it has on the kind of environment? Then what's the potential methods where we can reuse WCO other than cooking? Let's say after 3 cycles of cooking, we cannot reuse for cooking. So what are the other possible methods or possible ways we can use WCO to make something benefit product from it, right? So currently, if you see, many households dispose WCO in kitchen sink, at least 76%. That what the survey says. Now, these WCO has a potential to clog sewers and migrate towards water body. And as we all know, when the oil goes into the water body, it may actually affect the aquatic animals. And this oil being non-biodegradable, it also increases the water's biological oxygen demand, causing impact on the aquatic health. In addition, WCO also releases methane when disposed into soil. And we know that methane is having almost 25 times more potential of causing global warming compared to carbon dioxide. Right? Finally, WCO can also result in fire hazard if it is not properly disposed. So this way, there are multiple impact on the environment if you don't properly handle it or collect it and be disposed in a very non-professional manner. Right? If you see this picture here, this I just got on information where in Italy, this is what the amount of WCO is collected from one locality of around 40,000 people. You can see how it is varying with year. I mean to say, you can just see the number. It's around 8,000 kg, right? In a month, what the paper says, they're collecting this amount of oil for 40,000 people. Now imagine in India, we have 1.42 billion people. We can imagine how big numbers can be there. And second picture, you can see one where the person is cleaning the sewer due to clogging by WCO. So this way, the WCO or fresh cooking oil has significant impact on the environment, right? In the short and the both the long run. So going the potential usage, so recently, if you see, the Indian government has planned to use biodiesel to mix with the petroleum diesel up to 20%. Now, initially, they used to produce biodiesel with cooking oil or edible oils. Now, since WCO has been taken the attention of many environmentalists, so they plan to produce the biodiesel with WCO. How do we do it basically? To take a filtered used cooking oil, you can see the condition of cooking oil. It's almost black now. We cannot reuse it. So basically, after a process called pacification, we can actually separate or we can produce biodiesel, what we call as fatty acid methyl esters and glycerol. You can see this top portion is called FAME or fatty acid methyl esters. The bottom is glycerol. We separate them by gravity and get biodiesel, where B100 indicates the purity. So now, basically, this biodiesel can be mixed 20% with the petroleum diesel and can be used in the vehicles. But the problem is that to produce biodiesel, the cost is almost 1.5 to 2 times the normal diesel cost. Right. So obviously, it becomes uneconomical to produce in the long run. So we need to look into other possible ways that you can divert WCO into profitable product. Now, one way is that we can use mixtures and actually what is the asphalt mixture. Now, the asphalt mixture is simply a combination of aggregate and bitumen. We have all seen that our roads are being built with the bitumen and aggregate. So when you mix aggregate and bitumen, you get the asphalt mixture. Now, almost 80 to 90% of roads across the world are built with asphalt mixture because they're easy to construct, easy to maintain, and people have good amount of control on the properties and how to maintain them. Now, the production of asphalt mixtures also cause significant pollution in the long run, which leads to high carbon emissions. And finally, these asphalt payments also has limited service life. That means once you build a payment up to a certain period, maybe 15, 20 years, it will fail and you need to again rebuild the new road. So the question comes, whatever payment was built initially, what to do with that? Because we are spending aggregates, we are using bitumen and using natural aggregates. So should we discard it? Because they're natural materials. They cannot be produced at very small time frame. It takes millions of years to get them. So that's where the concept of recycled asphalt picture comes into the picture. Let's say you build a new road. This new road, after it undergoes failure, like cracks or renting or fatigue, some other kind of distresses, we can basically either dismantle it or build a new pavement, or we can mill it. There are very good technology of milling machines. We can mill it, get the recycled asphalt or recycled asphalt pavement, what we call RAP, and then stockpile it. And this recycled asphalt aggregate can be used in the road construction. Because the thing is that here, the pavement has failed, but the aggregates have not failed, right? The aggregates are still intact. Only the layer has been failed, the bonding has been failed, the asphalt has undergone significant hardness, with which cracks have occurred. But aggregates are still intact and of good quality. So when we use this recycled aggregate or recycled asphalt in the new pavements, the question arises about what about the hard binder existing on the aggregate? Now, generally, when we use recycled asphalt, we don't separate aggregate and bitumen. We directly add this black bitumen coated aggregate into the asphalt mixture. Now, since these aggregates are having aged binder coating, the stiffness of this binder is very hard compared to the new binder what we add, right? So that way, what the issue arises of blending between the recycled asphalt mixture and the new additional materials what we add. So this blending to happen properly or in a good manner, we use rejuvenators, aged bitumen into a proper unaged binder conditions where you can use in the asphalt mixture. Right. Now, when we include recycled asphalt and WCO, basically we get waste to wealth. How? Let us see. So basically, recycled asphalt and WCO are considered as solid waste because both are solid waste what we consider in general. Now, current practices in asphalt community permits up 25 to 30% of asphalt RA usage up to 25 to 30%. That means we cannot go beyond 30% of RA in the new asphalt mixture. So for example, if we're building a new road, we cannot consume more than 30% RA. The reason being, the recycled asphalt is having hard binder coating, so it may affect and cause improper blending. More the recycled asphalt content, more improper blending, and we won't be able to control the property of asphalt mixture. So generally the limit to 30%, but remaining 70% still is getting wasted. So people are trying to use, why can't we go to 70% or whatever more than 30%? So to more than 30% you want to go, we need to add rejuvenators. These rejuvenators actually, as told me, chemically alter. They chemically alter the bitumen composition because generally bitumen has four important components: saturates, aromatic, resins, and asphaltenes. Generally, for a aged bitumen, asphaltenes are higher, and for a let's say virgin or a fresh bitumen, asphaltenes will be in a controlled or a limited manner. Right. As you can see in the particular, as you can see in the particular figure here, the wrap is having high asphaltenes to maltings ratio. So it has more asphaltenes and less maltings, or let's say less aromatic, saturates, and resins. But if it's WCO basically it's having more maltings to asphaltene ratio. That means the maltings is higher. So by adding recycled asphalt and WCO together, we get a balanced binder, or let's say a binder which is having properties same to our required unaged binder. So this way, by using WCO, we can actually incorporate more amount of recycled asphalt in the bituminous or asphalt mixture and consume more of it rather than discarding it. But now, what challenges we can encounter when we use WCO as a rejuvenator? Let us see in short. So one is, let's say, variability in WCO. Now, we'll talk about WCO, cooking oil. There are n number of cooking oil like sunflower oil, coconut oil, palm oil, etc. So which one to use? Because in India, we have variety of foods, variety of cultures are there. So which kind of cooking oil should be used as a rejuvenator? The question of variability arises. Second thing, for a given construction project, we cannot use one for few kilometers sunflower oil or 3 kilometers other oil. It may cause problem in the kind of performance. So variability in WC becomes a big problem here. And second thing, should we go with single source or blended WCO? So what is single source? For example, you take one particular block or apartment block. In different houses, they use different kinds of oil. So let's say if the government plans to collect the cooking oil from different households, certainly they'll be collecting a blended WCO, which is having different proportion of different oils, maybe some amount of sunflower oil, some amount of mustard oil, some amount of palm oil, etc. So getting single source practically is impossible in reality, but mostly we encounter blended WCO when you want to get it for construction purposes. Next, on what basis can we select the WCO? Because as I told you, the WCO or cooking oil, cooking oil, we need to have some particular criteria. Generally, we come across value called as acid value or free fatty acid content, which you can use to select whether WCO can provide rejuvenation or not, right? And the by the blending. Even though the WCO modifies the chemical composition of bitumen, but how do we quantify it? Second thing, how it performs when we prepare a mix with WCO and residual asphalt. What are the performance characteristics? Because we generally look for performance like retting failure, fatigue failure, moisture damage, etc. So when we use any additional material or a new material, we obviously look for this characteristic so that the performance is well addressed before implementation. And finally, life cycle assessment. Are we getting any benefit by using recycled asphalt and WCO? And how do we quantify it? Right. So these challenges are what we're trying to address in IIT Bhubaneswar through one of our scholar Shobhit Jain. And he will discuss more about what technicalities we're trying to do with WCO and RAP to produce sustainable asphalt mixtures. Yes, over to you, Shobhit.
Yes, sir. I'm sharing my screen.
Sure, I will just unshare it.
So is my slides visible?
Yes.
Yeah.
So,
Thank you, sir, for this opportunity to share my work and briefing the topic so well. With the continuation of the introduction of the topic, researchers are assessing the potential of WCO as a rejuvenator, and they got success. But is it true that each type of WCO can be work as a rejuvenator? It is a big question. Therefore, variability of WCO is such important properties which should be investigated. This variability may be in terms of parental oil, acid values, or other physical properties. Other properties is controllable except the parental oil. Therefore, the variability of WCO in terms of parental oil were investigated in this study. First, the single source WCO was investigated for its rejuvenation potential. For this, we have collected different WCO from different sources with similar physical properties and acid values. Such, we have collected used mustard oil, used sunflower oil, and used palm oil. And these waste cooking oil were used to prepare the rejuvenated binder in the laboratory. The rejuvenated binders are the binders or the bitumen, which is prepared with the virgin binder, wrap binder, and the waste cooking oil. These binders were tested for the viscosity test, penetration, and the rating rheological parameters. And these were compared with the target binder, which we want to achieve in our laboratory, or that is also known as shown in my study, Anaged VG30 binder. The result shows that the binder with sunflower oil showed the minimum viscosity and the maximum penetration. This indicates that the sunflower oil had the maximum rejuvenation capabilities as it highly softens the binder. Meanwhile, the mustard oil showed the minimum rejuvenation as the binder with mustard oil showed the maximum viscosity and the minimum penetration. Further, in these all the binders, the wrap binder percentage is fixed, which is 60%. Similarly to these basic properties, the rating parameter of different binder was determined, and it was found that the binder with the sunflower oil showed the similar rating parameter as compared to our target binder, which is Anaged VG30. Further, the palm oil showed the better rejuvenation than the mustard oil, but it shows the lower rejuvenation than the sunflower oil. Further, for the chemical investigations, we have performed the Fourier transform infrared spectroscopy and the nuclear magnetic resonance test from the FTIR, which is Fourier transform infrared spectroscopy, to additional peak were found at 1650 and 1116 wave numbers. These peaks are related to the additional C-double-O bond stretches in the palm oil and the additional presence of the acid in the mustard oil, also known as the ericac acid. This acid is only present in the mustard oil, not in the palm oil and the sunflower oil. Similar finding was observed in the new NMR. The additional trio peak was observed in the case of mustard oil, which tends to the arechic acid. The arechic acid contains 22 carbons, and it was observed in the literature that the higher number of carbons possesses higher viscosity, which result in the lower adhesion between the WCO and the wrap binder, and finally it will be conclude in the lower resonation, lower adhesion between the WCO and the wrap binder. The collection of single source waste cooking oil is not practical in field, as it is important to access the resonation potential of blends of different WCOs, which is also known as the blended WCOs. For the investigations, different blended WCOs were prepared in the laboratory. 3 different blended WCO were prepared. In first, the used sunflower oil was kept in the majority. In the second, used palm oil was in the majority, and third, in used mustard oil in the majority. Like first is SO, second is MO, third is PO. In the SO, the sunflower oil is in the 50%, mustard oil 25%, palm oil 25%. In the MO, the mustard oil is in the 50%, sunflower oil 25%, palm oil 25%. And in the PO, the palm oil was in that 50% and other two oil were in 25%. The results of the rheological testing show that the resonation potential reduces as compared to the single source WCO. However, they show now considerable resonation. In the blended WCOs, the binder with the blended WCO with sunflower oil, which is SO, in which the sunflower oil is in the majority, shows the maximum resonation, followed by the PO and the mustard oil, respectively. It was observed that the binder with sunflower oil, majority of the sunflower oil shows similar rheological properties as compared to the unaged binder. It was observed from the rutting parameter that all the binders are showing the rutting parameter, which shows the higher temperature performance of the asphalt mixtures, asphalt binder. It shows the rutting parameter more than 2.2 kPa, which is the super pave criteria for rutting. But some researchers have claimed that the addition of WCO makes the binder more prone to fatigue failure or long-term failures. Hence, the fatigue life of the different binder was assessed in our study. In this direction, first the long-term performance of the resonated binder was assessed. For this, we have proposed a method to determine the optimum WCO content, which is a very critical parameter to get a good performance, which will be discussed in next slides. It was found that the resonated binders with the blended WCO showed significantly higher fatigue life as compared to the unaged WG30 after long-term aging. And it is irrespective of strain. At all the strain levels, we are getting good fatigue life for different resonated binders. And at the lower strain, the sunflower oil is showing the maximum fatigue life, and at the higher strain, the mustard oil had the maximum fatigue life. And from the stress strain curve, it was observed that the unaged VG30 binder showed the peak stress at the lower strain. Meanwhile, all the resonated binders showed lower peak stress and the higher area under curve, which represent the ductility nature of the resonated binder. Whereas the steep fall of unaged binder showed the brittle nature, which results in the lower fatigue life. So here this figure shows the proposed method to determine the optimum WCO for the different wrap contents. Basically, in the past studies, the studies mainly considered the physical or the rheological parameters, and they compared with the target binder. However, in our proposed method, we have considered two different criteria. The first criteria is the equiviscous criteria. As per this criteria, the viscosity of the short-term aged resonated binder, the viscosity of short-term aged resonated binder is similar to the viscosity of target binder in unaged condition. Here, the resonated binder was first short-term aged to simulate the field condition, as short-term aged binder is subjected to trafficking instead of unaged binder. This criteria was fixed to improve the fatigue life of the resonated binder, as the viscosity of resonated binder in the short-term aged condition is similar to the viscosity of target binder in unaged condition. However, this criteria may be resulted in the compromised rutting performance because the viscosity of short-term aged rejuvenated binder is similar to the unaged binder. So there is a high chance that our rejuvenated binder will show a good fatigue life, but it may not pass the superpave rutting criteria or the higher temperature criteria, which is the G star by sin delta should be greater than 2.2 kPa. In this direction, second criteria was chosen as the rutting criteria, that the rejuvenated binder, the short-term aged rejuvenated binder, should show the rutting parameter minimum of 2.2 kPa. From both the optimum WCO, minimum dose should be selected to have a good rutting performance. For the first equiviscous criteria, the viscosity of different binder at 135 degrees Celsius was determined and shown in the figure. The figure indicates that the higher addition of WCO reduced the viscosity of binder as it rejuvenates the aged binder. Meanwhile, the addition of an aged binder increased the viscosity of binder due to the hardness of the aged binder, as already discussed about it. With the addition of aged binder and WCO in optimum doses, the viscosity of unaged binder can be achieved, which is shown in figure by the red lines. The optimum WCO for different binders were evaluated with respect to the viscosity of the unaged binder or the target binder. The optimum doses were assessed for different binders with 75% rep, 60% rep, 45% rep, and 30% rep, considering the equiviscous criteria. The optimum binders, it means the binder with the optimum waste cooking oil, were expected to show the similar viscosity as compared to the unaged binder. Then in this direction, for the second criteria, the rutting parameter of different binder were determined, which is shown in this figure. The asphalt binder with a higher rutting parameter at a higher temperature shows a higher resistance to rutting. And this figure indicates that higher addition of WCO reduce the rutting parameter of binder as it rejuvenates the aged binder. Meanwhile, the addition of an aged binder increased the resistance to rutting of the rejuvenated binder due to the presence of the stiff aged binder. With the addition of aged binder and WCO in optimum doses, the limiting value, which is 2.2 kPa of rutting parameter, can be achieved. Which is also shown in the figure, that the red line shows the rutting parameter which meets the 2.2 kPa or 2200 Pascal of G star divided by sin delta. The optimum dose of WCO for different binders was evaluated based on the rutting parameter criteria of short-term aged binder condition, superpave condition, which is 2.2 kPa. I'm sorry. The final optimum WCO for the binders with 75%, 60%, 45%, and 30% aged binder will be a minimum of the optimum determined from both the criteria, and these the optimum values are shown in the table. Like higher the wrap content, higher the WCO is required. Further, a frequency sweep test or a rheological test was performed on the unaged binder and the optimum binders. Here, the optimum binders are the binder with the optimum WCO. This test was performed to assess the rheological parameters. The first figure indicates that higher at the higher frequency. Further figure shows that the short-term aged binder, STA binder, here STA binder is the short-term aged binder of the target binder, which is unaged VG30. That the figure shows that the STA binder of target binder and unaged binder showed the maximum and the minimum G star value at each frequency level. Further, all three optimum binders showed the higher G star value than the unaged binder, but lower G star value than the ST aged binder. The master curves demonstrate that the complex shear modulus reduces as the frequency decreases, as the loading time increases or the frequency decreases. This variation in G star for unaged binder are more significant than that of the optimum binders within the same frequency range. This indicates that the optimum binders have lower frequency sensitivity and the short-term aged binder, STA binder, showed the maximum G star value at each loading time, which indicates that the STA binder has a good higher temperature performance, but poor intermediate temperature performance. At the same time, the optimum binder showed the higher complex modulus compared to the unaged binder at a lower frequency, which implying that the optimum binders had better high temperature performance. Further, the optimum binders showed the lower G star value as compared to the unaged binder at the higher frequency, which indicates that it has also a good intermediate performance. In summary, the optimum binders performed better against both rutting and the cracking characteristics. Again, the FTIR spectra was performed on the unaged VG30 RAB binder and the rejuvenated binder at different wave numbers. The absorption peak of the RAB binder and the unaged VG30 were found to be very identical, and the peak intensity of the carbonyl group like COO bond and the sulfoxide group SOO stretch indicates the degree of the aging and the rejuvenation of the asphalt binder. As compared to the unaged VG30, the RAB binder had higher peak at the 1700 wave number and the 1031 wave number, which shows the higher aging of the binder. And the peak difference between the 750 and 800 centimeter inverse wave number shows the peak of the aromatic groups present in the binder. The maximum and the minimum peak of the aromatic group were found for the unaged VG30 and the RAB binder respectively. However, the intensity of unaged VG30 and rejuvenated binder was found to be very similar due to effect of the rejuvenation. The rejuvenated binder contains one additional absorption peak at the 1750 centimeter inverse, which shows the peak of waste cooking oil. Next figure shows the results of the quantitative analysis of the functional group indices. CI tends to the carbonyl index and SI tends to the sulfoxide index, which represent the aging of the binder. And it shows that the rejuvenated binder and unaged VG30 binder shows the similar CI and SI with respect to the RAB binder. As sir already discussed, that the improper blending between the RAB binder and the virgin binder is a critical concern, which significantly affect the performance of the asphalt mixture. During the service life, improper blending permits the water to entrap and result in the poor adhesion between the aggregates and the binder, which causes moisture damages. Also, improper blending between the virgin binder and RAB binder affects the coating quality. Hence, the moisture damage parameter was selected to determine the blending characteristics in this study. This does not mean that the poor blending only affects the moisture damage. It will also affect all the different failures. In this direction, the waste cooking oil was added in 3 different dosages. First dose is the optimum dose. Second dose is the optimum dose plus 2.5% dose. Third dose is the optimum dose minus 2.5% dose to determine the effect of WCO doses. Also, the WCO as was introduced in different 2 ways. First way is the direct addition or the dry method, and in the second method, instead of WCO, softer binder was added, which is also known as the indirect addition. It was found that the recycled mixture without any WCO, which is the case R, without any WCO, it was found that the recycled mixture without any WCO showed the minimum PSR value, which indicates the minimum blending or the poorest blending between the virgin and the RAB binder. Further, adding WCO increased the TSR value, which also indicates the improvement in the blending or the enhanced blending. This addition is more effective in the form of dry addition or direct addition of WCO in the recycled mixture. The dry method results in the direct encounter of WCO to the RAB mixtures, which possesses good rejuvenation. Here, the green line shows the minimum TSR value requirement, which is 80% as per the OSTO T283, and the black line shows the TSR of the conventional mixture, which is HMA. The recycled mixture was unable to achieve the TSR of conventional mixture, but it was able to achieve the minimum TSR with optimum WCO and dry method. In addition to the tensile shear strength ratio test, which is the we have performed for moisture stability, moisture susceptibility, where the optimum dose of WCO resulted in the higher TSR, a similar investigation was performed with the reference of the Rutting test. The asphalt mixture with 60% 60% rep was produced with different dose of WCO. As the like M is the medium oil, it means the optimum dose. L is the low oil, it means optimum minus 2.5%, and high is the optimum plus 2.5%. For the comparison purpose, we have also produced the slab of HMA. HMA without slab, the rud depth of different asphalt mixture is shown in this figure, and it can be seen that the mixture with higher and lower WCO doses showed the highest and the lowest rud depth respectively, which was also observed in case of the binder testing. The higher rud depth could be attributed to the excessive softening of the binder due to the higher doses of WCO, while the lower rud depth could be due to the insufficient rejuvenation, where a stiffer binder excesses in the mixture. It was quite interesting to observe that the hot mix asphalt, which is our conventional mixture, and asphalt mixture with optimum WCO doses had similar rud depth for a given cycle. So this is about the rutting and the moisture susceptibility. Now the rutting of the optimum mixtures with different rep contents was evaluated in this section to assess the higher temperature performance. Also, with those mixtures, we have prepared one more mixture, which is the recycled mixture without WCO for the comparative purpose. The increase in the rud depth with a number of cycles is shown in the figure. It was found that the recycled mixture without WCO showed significantly lower rutting as compared to HMA. It is credited to the presence of the aged binder in the recycled mixture. Further, as compared to the recycled mixture with WCO without WCO, the other optimum mixture showed higher rutting, which is similar to HMA. And another figure which shows the dynamic stability of different mixtures, where the dynamic stability represents the higher resistance to rutting. Dynamic stability can be defined as the number of cycles to produce unit rud depth. And from figure, it was observed that the recycled mixture without WCO showed the significantly higher DS value. Further, optimum mixture showed almost similar DS value as compared to HMA. The cracking potential, which is the another failure for the asphalt mixture, the cracking potential of the optimum mixtures, HMA, and the recycled mixture without WCO was evaluated as shown in the figure. And this was evaluated by perform the ideal CD test, which is the ITL cracking tolerance test. And in this test, we have the CT index was assessed to evaluate the resistance of the mixture against the fatigue cracking. The higher CT index represent a higher fatigue resistance and vice versa. From figure, it was observed that the recycled mixture without WCO had showed a higher peak load as compared to the HMA and other optimum mixtures. However, it showed very less displacement before the failure. As compared to the others. It may be credited to the presence of the aged binder, which renders the mixtures more stiffer and less ductile. All the optimum mixtures showed similar curves as compared to the HMA. It could be because WCO had a rejuvenating effect on the aged binder, which allows more displacement without failure of the recycled mixture with wrap and improves the ductility of the binder. From the next figure, the greater the CT index, the greater the cracking resistance. And it was also observed in different NCHRP reports. It was found that the recycled mixture without WCO showed the rust cracking resistance. Moreover, the optimum mixture showed good even better cracking resistance than HMA. For the life cycle assessment part, This method used the cradle to gate method, which includes the stages of the production, transportation of raw materials to the mixing plant, manufacturation, transportation to the site of the asphalt mixture, compaction, and the laying process, respectively. This was accomplished since there was no data available on the serviceability and the end of the life phases of the pavement with the RAP and WCO systems. For each of the stages, the Central Pollution Board and some Indian Construction Materials Database construction agencies were among the sources of the data used to make the life cycle inventory. The stages considered in the studies shown in the figure, and the analysis was done for the pavement having a length of 1 kilometer, width of 3.5 meter, and only the construction of the surface layer having a 50 thickness was taken in this study. In this study, we have considered two impact factors, which is the total embodied energy and the greenhouse gases emissions. This inventory values were taken from the government agencies, as earlier told, and the literatures of the for different materials and the processes. For the further analysis, first the quantity of different material was calculated for different optimum mixtures and the conventional mixtures, which is HMA. And these weights or quantities was calculated with the help of densities determined in the laboratories. Further, the emissions related to the transportation of materials were assessed, and it was observed that using RAP resulted in the lower emissions of natural materials related to the transportation, but it results in the higher emissions of transportation of RAP and WCA. It was found that the utilization of RAP reduced the greenhouse gases and total embodied energy considerably, because it saved the production of virgin material. It saved the production of virgin materials, which results in the lower energy consumption, emissions as compared to HMA. When RAP is used, it needs to be milled and screened, as Sir earlier told, which is also known as the processing. And it also needs to be transported from the field to mixing plant and then to the construction site. This uses additional energy and leads to uses additional energy and leads to pollution. It was observed in the study that the transportation of RAP adds a major portion of total embodied energy and the greenhouse gases as compared to the processing of the RAP. Therefore, the transportation of waste cooking oil and RAP is a crucial parameter to analyze the life cycle assessment of the optimum mixture and HMA. In addition to this, the transportation distances for the RAP were taken from 100, 300, 500, and 700 kilometers to evaluate the allowable or the permissible distance for the RAP transportation, and also to determine the trade-off between the distance and the RAP quantity. From figure, it was observed that the transportation, From figure, it was observed that the transportation of RAP does not affect the total embodied energy as compared to the GHG significantly. The optimum mixture showed the lower total embodied energy as compared to the HMA, irrespective of the distances of transportation of RAP. However, the higher inclusion of RAP resulted in the further reduction in the transportation total embodied energy. Same as the environmental analysis, the economic, I think I forgot a slide. I forgot this thing. Let me. This figure shows that the GHG emissions of different optimum mixtures of HMA, which takes account the effect of distances that RAP has to be transported. Here, the D is the distance of the RAP source from the mixing plant. The waste cooking oil is easily available as compared to the bitumen and the RAP. But for the worst condition, the transportation distance for the waste cooking oil was taken as 400 kilometers in our study. Also, the quantity of WCO is very less as compared to the different materials. Hence, it does not affect the total embodied energy and greenhouse gases emissions significantly. Further, for the mixtures with 30% RAP all the distances are safe, but for the mixtures with 45% rep, the distance 700 kilometers is not safe. For the mixtures with 60% rep, the 500 and 700 kilometer distance is not safe, and for the 75% rep, the 500 and 700 kilometer distance is not safe when we talk about the GHG emissions. The optimum mixtures, different mixtures showed the 700, 500, and 300 kilometers respectively to achieve the GHG emissions equivalent to the HMA or the lesser than the HMA. Now, okay, this I have completed. Yeah. Same as the environmental analysis, the economical analysis was done for the 1 kilometer of road span having 3.5 meter width and 50 mm of the wearing course. The cost of different materials, transportation, diesel were taken from the Delhi Schedule of Rates, which is DSR Volume 1, to calculate the transportation cost. First, the number of the trucks required to transport the material has been calculated, and the capacity of the trucks were taken from the field implementations. These are the rates of different materials we have taken from the DSR. Now the figure shows the cost of the different optimum mixtures and the HMA, which is the conventional mixture, with a transportation distances of 100 km and permissible distances. It was observed that the cost is reduced with the increase in the RAP content. Mixture with 75% RAP and conventional mixture showed the minimum and the maximum cost respectively. Further, the optimum mixture with permissible distances showed the higher cost as compared to the optimum mixtures at 100 kilometers, but lower than lower than HMA. The cost saving of the mixture with different RAP contents were showed in this figure, and it's what observed that with the higher inclusion of RAP in the asphalt mixture resulted in the higher cost saving, and this cost saving also depends on the permissible distances of the transportation of RAP. Like lower the distance, higher will be the cost saving. Now comes apart the conclusion. The RAP utilization in our asphalt mixture is a sustainable approach as it reduces the demands of natural materials, which results in the lower energy consumption, fuel consumption, emissions reduction, and cost saving. Despite from these advantages, the RAP contains the aged binder, stiff binder, hard binder, which degrades the performance of the mixture with RAP in terms of cracking, which may be low temperature cracking or intermediate temperature cracking. The WCO as a reservoir is gaining attention in the pavement industry as it can significantly restore the properties of RAP binder. In this research, we have covered the variability of WCO blending properties and the performance. It was found that the recycled mixture could perform similar or even better than the conventional mixture if the appropriate dose and good quality of WCO is added in the mixtures. Further, this utilization of WCO in the asphalt mixture again solves the problem related to the disposal issues, which is the main concern as discussed by the sir. And this reutilization of WCO can be reduced with the utilization of WCO in the asphalt pavement industry, which can affect the human life. It was observed from the cost analysis that up to 37% cost can be saved by utilizing only 60% RAP in the construction. In summary, the addition of RAP and WCO in the asphalt mixture can purchase very healthy economic and environmental benefit without compromising the performance. Thank you, sir.
Is Shobit, Dr. Ravi?
Yes. Hello, am I audible, sir?
Yeah, Shobit, you're audible.
Yes. So Subhajit, it's like Anushji, are you ready to take questions now?
Yeah, yes. I already see some questions in the chat box.
Okay. Yeah, so that is done. We can start the discussion also.
So one question from Joydeep Taran is there. Where the question is like waste cooking oil has a problem of clogging due to sticky nature. How we are overcoming this problem in blending? So yeah, basically WCO what we use generally, what we see is not too much sticky. It might have turned black, but it's not sticky like a glue or something like a thick liquid. It is still reusable for rejuvenation purposes. It won't be so much difficult to use. Only concern is that we need to see what is the amount of acid value and free fatty acid content. Because if it is having too much high amount of free fatty acid content or acid value, it may impact the moisture damage resistance. So that way we can, if it is too much having very high acid value, we can reduce it by different chemical methods. If it is below a particular value, like 1.5% or 2.5%, we can go ahead with the rejuvenation. That's what we found in our study also. And what impacts of WCO drainage of roads? Drainage of roads and WCO, I don't know, are you referring to leaching of WCO? Leaching, we haven't tested, but if it is water drainage, certainly in payments we give chamber. So it just functions as a normal payment only. That's not be a problem. And other question from Raki sir, I would like to know how we can decrease the gap of cost of production. It's 1.5 to 2 times for normal diesel. Now, this cost is for biodiesel, not for WCO. Now, if you want to produce a biodiesel, we use WCO as one of the primary input, right? Where we use certain methods using alcohol like ethanol and other materials as a catalyst and produce the biodiesel. Now, that is quite expensive. That's what we mentioned in the presentation. So regarding measures, how to reduce it, I mean, we haven't tested it, but that's not in our purview. Certainly, we can look into the methods or how we can reduce the cost to produce biodiesel also. Is Dr. Ravi?
Yes, Anush. Participants, do you have any further questions for discussion? You can unmute yourself and ask. The session is open for interaction.
I think no more questions. I don't see questions in chat box.
Yeah, chat box questions are done.
Yeah.
Anush, can you put some thoughts on? It's like although it's like from a waste management point of view, collection of this cooking oil, then transporting it to a specific location, and setting it up. There is an upstream process to bring once you are moving it from laboratory scale to field scale. So, any thoughts on how this can be possible?
So already there are few startups which are collecting W production currently. Recently, I came across an article where one person has earned several thousand crores collecting WCO through because collecting it is a big challenge, obviously. So that person is trying to produce biodiesel by collecting WCO in a very proper engineered manner. Because obviously, in future, biodiesel may play a big role in terms of fossil fuels. That way, biodiesel is, people are trying to look into more how to collect WCO in a very engineered manner.
Okay. And there's one question from, one more question from Rakesh Share. What are the parameters as viscosity and penetration only were taken specifically? Could other parameters also contribute?
Yes, already as Shobit discussed, we taken several other parameters like G star or stiffness of bitumen into consideration. But viscosity and penetration, common parameter, what it is for bitumen basically. We talk bitumen, we talk about viscosity and penetration. So to make it simple, we have taken those two parameters. And to make it more complex, we took G star and other parameters.
And one more question from Jaideepa.
What pre-treatments?
Any pre-treatments given to WCO after its collection?
Yeah, it's a good question actually. I think Shobit can also answer this. So generally what we do when, as I told you, if the acid value and FA of WC is quite high, we can transisterify to reduce the amount of free fatty acids. That's what currently is being done. We also have done that by, if you take any oil which is having very high acid value, we transisterify it and decrease the acid value and then use as a rejuvenant. Shobit,
Yes, sir.
you want to answer the question? Are there any pre-treatments given to WCO operates collection?
Yeah.
One is filtering.
Yeah, actually, I can answer it. Actually, there is a very important factor, as sir told, that the acid value of the WCO. Like if we are collecting the WCO, which has been used 2 or 3 times, it can be considered as a rejuvenator. So for that purpose, we can use this WCO directly. But if you are using the WCO, which has been used multiple times, 5, 6 times, which has very higher acid value, we have to pre-treat it, which is also known as the like transesterification. So like I have used the WCO with lower acid values. That is why I didn't use the transesterification. So if you are using the WCO with the very poor quality, we have to pre-treat it with the transesterification. I hope I am able to answer you, Jaideep.
And Jyoti, to add more, as Shobit told that most of the food agencies like FSSAI, they won't allow you to reuse cooking oil more than 3 times. Let's say you take any restaurants or any food eateries, they cannot use it more than 3 times. So obviously, generally what we have found from our study is that so the free fatty acid value and the acid value in the eatery junctions is mostly within the limit required limits. So you don't need any pre-treatment to use as a rejuvenator. Once you filter it, you can go ahead with the rejuvenation. That's what we have found from local eateries and other public hostels, what we collected from Delhi.
Okay, thank you so much, sir.
Yeah. So, any more questions, participants? Yes, Dr. Ravi. Hello.
Subhajit, can you unshare your screen?
Yeah, sure.
So if there are no further questions, so it will be a great time that we'll be winding up our day 3 session. So thank you, Dr. Anushji, for taking your valuable time out of your hectic schedule. And it was a nice presentation for us in looking at all perspective of including material looking in, plus decarbonization aspects where you're in overall system. So we thank also Subhajit, who has conducted this particular research and projecting your team over here. So next time we would love to see you on the campus and hear you offline. So thank you for joining us.
Thank you very much for the team to call me for the lecture. And I also thank the participants for good questions what they have asked. Thank you very much. So I think I'll be leaving the meeting now.
Yes.
Okay. Thank you.
Thank you. So dear participants, this we come to an end of day 3 on the capacity. Have an energizing day and get yourself refreshed and refueled till 10 o'clock tomorrow to have a very beautiful sessions back to back tomorrow also, where the first session will be on energy storage and batteries for electric vehicle charging infrastructure, being delivered by Professor Amarish Chandra from Department of Physics, IIT Kharagpur. And the next session will be on development of a sustainability assessment framework, focus on alternative fuels, from Associate Professor Wahidul Piswas from Sustainable Engineering Group, Cotton University. And then we'll look in the afternoon session, we'll be looking in the biofuels in India, with an overview on its applications, listening from one of the key persons in the biotechnology department and across the country, Professor Ramakrishna Sen from IIT Kharagpur. And in the evening, the fourth session, we'll have an industry connect with Mr. D.M. Giri, who is a founder, advisor, and scientist of ASN Fuels. Will be speaking on his perspectives from circular economy in biofuel sector with a focus on rural biomass economy and connecting that particular RB blueprint in the Indian doors, focusing to the village doorsteps. So with this, we conclude the so see you.